Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at continuity. This is section 2.6 in the book. I believe it starts around page 103. And it begins with giving us a really elegant definition of continuity. And it says a function is continuous at a if the limit as x approaches a of f of x is equal to f of a. So just by hearing that or looking at that, it might not look like much, but there's really kind of a lot packed into this simple definition here, and let's see what that is. First of all, the limit of this has to equal to the function defined at that. So that first of all implies that the function exists at the a at some value, that the limit is equal to some value, and that's going to mean that both the left side and the right side limit are both going to have to equal that value, since the limit actually exists and equals that value. So a lot of stuff going on, and we've got a checklist here to kind of talk about what it means, kind of what I just said here. But in order for f to be continuous at a, all these conditions must hold. So our function is defined at a. That means a is in the domain of f. The limit as x approaches a exists, which implies that the limit from the right hand side is equal to the limit from the left hand side, which is the same. And then the final part of this is the limit as x approaches a from both sides has to equal whatever the function is defined at that value. So let's go ahead and take a look at continuity, or look at an example here. Alright, so looking at this graph here, let's find out all the points where it is and is not continuous. Let's try to take a look at, see if we can figure out what's continuous and what's not continuous. All right, so let's start with x equals 0. Well, if we go up to x equals 0, we have a hole there, which means it's not even defined at x equals 0. Therefore, the limit does not exist because of that. Also, if we look at the limits from the right of x equals 0, the y value is approaching 2, but there's nothing from the left. And since the right side and the left side limit are not equal to the same value, the limit does not exist. So for multiple reasons, this graph is not continuous at x equals 0. How about 0.5? X equals 0.5. Well, right there we're going to have a y value right about here. And we look that from the left side, it looks like we're approaching 2.5. From the right side of x equals 0.5, it looks like we're also approaching 2.5. So the limit's going to exist, and it's going to be equal to 2.5. So in order for it to be continuous here, this function also has to be defined at x equals 0.5. And when it's defined there, the value of y has to be 2.5. And it is, because if we were to put in 0.5, we go right up here, and it looks like it's defined right here at 2.5. So this meets all of the conditions for being continuous. Now, one visual way, or more conceptual way that I like to explain it, is in order for it to be continuous, you have to be able to take your pencil from both sides, starting from one side of that value, and move to the other side of that value without lifting your pen. So let me kind of give you a quick example of that. So let's say here is 3. X equals 3. Now, if I want to find out if it is continuous at x equals 3, I have to be able to start from the, let's draw a little line up here. I have to be able to start from the left side of x equals 3, go all the way to all the way to 3 and then move to the right side of 3. As long as I can do that without lifting my pencil or pen, then it's going to be continuous at x equals 3. Just like 0.5 down here. If I start from the left side of 0.5, I can continuously draw a line over this to the right side of x equals 0.5. Therefore, it is continuous there. It doesn't even have to be smooth. It can be a sharp edge like that. But as long as I can move from one side to the other without lifting my pen, then it is continuous. So if we were to apply that to x equals 1, if I start to the left side of x equals 1, I have to go here, but then I have to lift my pen at x equals 1 up here and then lift it again. So since I can't get from the left side of 1 to the right side of 1 without lifting my pen, then it is not continuous at x equals 1. And the reason it isn't, because of this checklist here, is because the limit as x approaches 1 is equal to 3, but the function evaluated at 1 is equal to 4, and 3 is not equal to 4. That is why it is not continuous. How about at 2? Well, from 2, if I start from the left side, I go down here, but then I have to lift my pen and come up here from the right side, so this is also not continuous. And for this one, it's because the left-sided limit here is 2, the right-sided limit is 3, and since the left side and the right side are different, then the limit does not exist there. And then for number 3 here, once again, if I start from the left side and I come to the right side, I have to lift my pen right there because there's no value there. So it is also not continuous at 3, basically because it is not defined at 3. So hopefully this makes a little bit of sense, but definitely need to do some practice ones. So let's move on to the next part. Okay, so for the next few theorems here, 2.9 through 2.12, it's basically just giving some rules about continuity. This is something that you can read over, look at the examples in the book, make sure that you understand them. We'll talk about a couple of them, but this just, the first one here just says if f and g are continuous at a, then the following functions are also continuous at a. Assume c is a constant and n is greater than 0, is an integer. This is, alright, so basically the sum of two continuous functions, well, that's also going to be continuous. The quotient of two continuous functions, that's also going to be continuous as long as the bottom function is not equal to 0. So on and so forth. So take a look at those. Polynomials. Polynomials are functions that are continuous for all values in the domain, and hopefully we know that polynomials have a domain from negative infinity to positive infinity, so they are continuous everywhere. And then they talk a little bit about rational functions. And then we kind of lead to composite functions. Hopefully we've done some composite functions in pre-calculus, but if we're looking at the functions and they're continuous at g of a here and at f, then if we take the composite of those two functions, that's also going to be continuous at a. And that's what we'll take a look at an example of right here. Alright, so let's take a look at this first limit here. The limit as x approaches 1 of the function x plus 5 divided by x plus 2, all raised to the 4th power. Now we can really look at this as two functions. So the inside function here we could write as g of x. So we could say, g of x, call that the inside function there, is just x plus 5 all over x plus 2 plus 2. And then f of x is just the inside here. We'll call that just x raised to the 4th. Right? And that way, if you were to write this function as f of g of x in composite form, you would get this function back here, right? Because the g of x goes on the inside, it would be going here, and then the whole thing would be raised to the 4th power there. So taking a look at this, the first thing we need to do is make sure that the g of x is continuous at a. So if we put in the 1, which is our a, we're going to get, so g of 1 is equal to, that's going to be 6 over 3, 6 over 3, which is equal to 2. And then we need to make sure that the next function, the f of x, is continuous at 2. And if we put in f of 2, there really shouldn't be an equal sign there, but f of 2, just put a comma there, that's going to be equal to 2 raised to the 4th power, 2, 4, 8, 16. So that'll be 16. All right, so both of these exist and are continuous at both of those, so we can rewrite our limit like this up here. So this limit here, we can rewrite that as the limit as x approaches a, or x approaches 1 in this case, of x plus 5 all over x plus 2, and the whole thing raised to the 4th power. So that's basically what we're doing. We're taking the limit of the composite function, and then we are just finding the limit of the inner function, and then taking the outer function there, just like this. So we already know that the limit as x approaches 1 of this is equal to 2. So this is just going to be 2 to the 4th, which is, of course, 16. And that would be our answer. All right, and the last thing I wanted to talk about here is Theorem 2.16. This is the intermediate value theorem. And it says, suppose f is continuous on the interval from a to b, and L is a number strictly between f of a and f of b. Then there exists at least one number, c, in AB satisfying f of c is equal to L. So what does that mean? Well, we have a quick graph here. So we have a continuous interval from A to B, and let's talk a little bit about what that means. Continuous over an interval means that it contains the endpoints there, and that that you can get from my mouse is messing up. You can get from one point to the other without lifting your pen at all. So we can go from A to B, from the A endpoint to the B endpoint without lifting our pen. So that basically means that this function is continuous on this interval. And now if we mark f of a and f of b, f of a is just the y value at x equals a, f of b is just the y value at x equals b. If we take any value L, so just some value between f of a and f of b, then this theorem here guarantees us that there's at least one x value in this interval here, strictly, or in this interval, that if we take the function at that c, we're going to get that L back. Yes, it sounds a little bit confusing, but we're actually going to be using this in a couple of sections from now, so make sure that you take a look at it and we understand what it's saying, and we'll take a look at an example of it as well. Alright, so I'm going to be looking at, this is number 67 in the exercises, and here it says applying the intermediate value theorem. A, use the intermediate value theorem to show that the following equations have a solution on the given interval. B, using a graphing utility to find all the solutions to the equation on the given interval. And then we want to illustrate our answers with the appropriate graph. All right, so we have this function here, 2x cubed plus x minus 2 is equal to 0. And we want to use this theorem here to show that we have at least one solution on the interval from -1 to +1 here. So first of all, we need to make sure that this function is continuous over this interval, and hopefully we know from this section and prior sections that polynomials are continuous for all values of x, and this is a polynomial. Therefore, this is definitely continuous from -1 to +1, since it's already continuous from -infinity to +infinity. All right, so that tells us that in the interval from -1 to +1, we are guaranteed at least one solution. We're guaranteed at least one solution. And then we're going to use a graphing utility here. So let's go ahead and pull up the graph. So y equals, and then we're going to put that into x cubed plus x minus 2. And so there is my function. And I'm looking on the interval from -1 to +1. So I'm going to go over to my window. And we're going to change the x values from -1 to +1. And let's go ahead and look at that graph here. And so this is what it looks like. And we're trying to find at x equals 0. So we're trying to locate that value there. Now it looks like there's only going to be one solution. There's only going to be one solution here. So go ahead and see if you can figure out what that solution is. We'll pause and then we'll come back. All right. So remember, this function here is equal to 0. So that means our y value is going to be equal to 0. So we're trying to find this intersect here. This would be the x-intersect of where the function goes through. And like I said before, it looks like there's only going to be one solution to this. So how do we find that x-intercept using the graphing tool? Well, you go to second calculate, and we're going to do the we can do the 0 function here. And we need a left bound and a right bound. It doesn't matter as long as one is on the left and the other one is on the right side of it. Something like this. Do I want to guess? No. And my x value is 0.8351223. So that's how I can find my solution there, and I can visually see that it's only going through the x-axis in one place. It says illustrate your answer with an appropriate graph, and this here would be the appropriate graph. Now remember, the intermediate value theorem only guarantees the existence of at least one number. So it could be 2, it could be 3, it could be an infinite number. So just keep that in mind. All right, everybody. Let's see if we can do one more problem before we finish up here. All right, let's give this one a try. This is number 44 in the book. It says determine the intervals on which the following functions are continuous. At which finite endpoints of the intervals of continuity is f continuous from the left or continuous from the right? All right, so we have this square root here. Now remember, this function is going to be defined for all values that are 0 or greater inside the square root, because if we have any negative numbers in here, then we try to take the square root of that, and that's not going to be in the domain of our function here. So what I want to do is I want to find out at what values is this thing positive and what values is this thing negative. So let's go ahead and set the inside equal to 0, because that will tell me the points at which it changes from positive to negative. So let that equal 0, and then we could factor this into x minus 2 and x minus 1 is equal to 0. Therefore, we have zeros at x is equal to 1 and x is equal to 2. So this means that if we look at a number line here, look at the number line, we have 0, 1, and 2. I want to take a look to see what the sign is below 1, and then between 1 and 2, and then above 2 here. I could have 3 different signs depending on the multiplicity here. Alright, so I'm going to use my calculator for this because I like to use my calculator. And we're going to go to y equals, and I'm going to put the function in there. So this is the square root of x squared minus 3x plus 2. And now I'm going to go to my second window, make sure I'm on Ask and Auto because I'm going to use my table for this. And then second table here, let's delete those out. And the first thing I want to do is just verify that 1 and 2 are 0. So if I put 1 in, I get a 0. I put 2 in, I get a 0. So that just kind of verifies those answers. And then I want to look at points in these 3 intervals here. So let's take a point that is less than 1, so 0, and we get a positive number. So I'm going to put a little plus up here. And then I'm going to take a value between 1 and 2. I'm guessing I'm going to get a negative number, but we shall see. Let's take 1.5. Any number? Oh, I can't do 1.5. How about 1.3? No. So why can't I do that? Because it's making it negative. I probably should have just put in the function without the square root, but error means that it's trying to take the square root of a negative number. So I'll put a minus, and then if I put anything above 2, it should work. So let's do 2.4 or 100, and we get positive numbers. All right, so what does this mean? This means that this function will be continuous using any endpoints from negative infinity down to positive 1. And let me just double check here. Just want to see how we write that. And it really should be written like this. Hold on just a moment here. And we can also go from 2 to positive infinity. So as long as we use both of our endpoints either in this interval or both of our endpoints in this interval, then we will have continuous intervals there. All right, guys, I hope this helps. If you have any questions, let me know, and have a great rest of your weekend.